Today's topic, integration by u-substitution and pattern recognition. So Corpy likes this pattern recognition thing. When we get into it, if you guys want to go with it, it's actually better, it looks like, in the long run. I think if we were going on to maybe take Calc B or BC, or maybe if you're going on to be an engineer or something like that, you're going to do a lot of integrals, maybe this would be better. But I think u-substitution is probably the best method to get us going here. So anyway, let's start by doing some review. I'd like you to pause and take the derivative of this function. All right, let's see how you did. So hopefully you notice that this is a chain rule. So who's our outside function? It's tangent. So the derivative of tangent is, sorry, I said it wrong. The outside function is tangent something. So the derivative of tangent something is secant squared something. Times, okay, now our next layer, so if you want to, you can go over here, cross out tangent like we used to do. So we've derived that outside layer. Our next outside layer is e to the something. The derivative of e to the something is e to the something. So this would be e to the 4x squared times. You can go back here, cross out the e to the, and I have 4x squared. Derivative of 4x squared is 8x. Now we might want to try to organize this so it looks a little nicer. So I'm going to push the 8x out front. E to the 4x squared, secant squared of e to the 4x squared. And box it in and put it up on my fridge. Feel all warm and fuzzy inside. Remember when that was the whole problem? You'd just be done? Oh, those are the days. Okay, so our topic is integration. So let's try to integrate this mess. We'll integrate 8. Oh boy. I know the integral of this. I know the integral of this. I know the integral of this. But I don't know the integral of all those put together. So is there a chain rule or something that we could use that would figure this out? Well, yes, there is. And that's the part that's the u-substitution that we're going to point out. But I want to point out, look up here. What do you notice? So when we took the derivative of this mess, this chain, we ended up with this. So if I wanted to integrate that, what would we get? Pause, give it a try. All right, pretty obvious. It would be tangent of the quantity e to the 4x squared, right? Wrong. What'd you forget? Plus c. This is an indefinite integral, so we're not plugging in those two values, the top value and the bottom value of the integral, so we got to write our plus c. Now, if you're ever not sure about this, what we could do now is we could check by taking the derivative. Okay, so how do we do this? And obviously, we did this derivative, and so it was pretty easy to work backwards once we had already done this. But what happens when we get this without already having done the answer, basically? Well, here's the sort of trick. Here's what you want to do. You want to kind of highlight the messiest part first. So if you were to highlight what would be the nastiest piece of this, or the outside, the most outside of the function. So this is just a term. This has an outside function, right? But this has an outside function that's even nastier than this one. So this, in the outside function, the inside of this is e to the blah, blah, blah. The inside of this is just 4x squared. This doesn't have an inside, or if it's x, it's just 1. So what you want to do first is we want to find the outside function. Now, once you find the outside function, you can start to derive this thing. Well, this is what type of a rule? This is a chain rule. And then you're going to find that when you derive this, that the derivative of this is going to be one of our other functions, which then you would do the chain rule again and again and again. So our goal is we're trying to find the outermost, messiest piece, and we're going to do this where we're going to sub this piece out to make this look a lot nicer. It's not too complicated. It probably sounds a little bit messy. So here's some stuff. I think it's easier to just look at some examples to get going. So I'm going to skip right to More stuff, u-substitution. I think this is worthwhile to start to highlight in here. So when I talk about u equals g of x, okay, that g of x, what we're calling u, that's the inside function. G of x is the function on the inside. And then du, well, if u is our variable, du would stand for the derivative of u. Du is the derivative of the inside function. And we get that we're going to take our function that's super messy, like all this mess up here. We're going to take this g of x, we're going to replace it with u. We're going to take this derivative g of x, d of x, and that all gets rolled together. Let me try to highlight some of this. Actually, I'll do it with colors, I think. So g of x gets designated as this u piece. And then these two things together, g prime of x and d of x, roll together, and they get subbed into this thing that's called du. See how over here, du is the derivative times dx. So those two things get mashed together, and they get hidden in this thing called du. And so this becomes something pretty easy to integrate. The integration of little f is big F. And so let's show you with an example. All right, so he's talking about we're going to use this dummy variable u. Now, there's two ways to do this. He does this with pattern recognition, and he does this by UDU. I'm going to do almost everything by UDUs. I think that that's, to me, a lot easier. So, all right, well, let's take a look. So we want to integrate this thing. Well, we do actually, technically, we have the skill to integrate this right now. I don't want to. What could we do with this so that it's not a composed function, so there's not layers? I could expand this using Pascal. It's Pascal's triangle. That would be a term that's what? How many? What, 13? That would be a polynomial that's 13 terms long. And then we'd have to distribute as well. Ugh. If you want to, go for it. Have fun. I'm going to use the UDU substitution. So I want to pick what u is. U is my inside function. So looking at this piece, I kind of feel like there's two things inside because I got two things inside of parentheses. You usually want to pick the most complicated piece. So this is more complicated than this grouping. So I'm going to start with this as my u. So u is equal to x squared plus 1. Remember, u is your inside function. And then we're going to identify du, which is the derivative. Remember how we write dy dx? So this is technically well, I'll show you in a minute. Du is the derivative of this. So what's the derivative of u? Du. What's the derivative of x squared plus 1? Is 2x dx. So normally we would write this like this. Remember how we wrote dy over dx? So this would be du over dx equals 2x. This is connected by division, so I just multiply that to the other side. If you want to write it out this way first and then multiply over, feel free. Okay, so how does this help us? Well, now go back to your integral. We're taking now the integral from, the integral of x squared plus 1. But what did we call x squared plus 1? We called that u. So now I can take that out and replace that as u to the 12th instead of x squared plus 1 to the 12th. And then here, this takes kids usually a little bit of time to figure out. This gets a little bit sneaky. Maybe you'll see it right away, maybe not. This together, 2x dx, gets rolled into the du. So that just becomes a du at the end. So du actually has, like, inside of it, sub for it, 2x and dx. That's where that part went. So this piece got hidden inside of the u. The 2x and the dx, which is equivalent to u, got replaced with du. Now, we don't have x's, but we now have an equation or an integral that's really easy to calculate. So this would be u to the 13th over 13. Is it definite? No, it is not definite, so don't forget your plus c. And then now, I can take this u value and I can put it back in to give me the integral, the antiderivative. And look, you can check this if you're not sure. If you don't believe that this is true, check it. Take the derivative. Okay, when I derive this, this is a layered function. This is something to the 13th is my outside function. So what's the derivative of something to the 13th? 13 something to the 12th. That's a constant, so that's not going to change. What's the derivative of c? 0. That's gone. My 13s cancel. What am I left with? Sorry. I didn't finish my chain. So I got to do the derivative of the inside. So derivative of something to the 13th is 13 something to the 12th times the derivative of the inside, which was 2x. And then my 13s cancel, and we get exactly what we had before. So nice about this is you can always check, see if it's right based on taking the derivative. Okay, so I'm going to try to show you this pattern recognition method, see if you like it better. Like I said, I'm not good enough with my derivatives to just be able to see it all. So I'm going to do it with u du first, and then we're going to check it out. So what would u be? U is always your inside function. Your inside function inside the messiest piece. So this part looks the nastiest. So I'm going to have 2x to the 4th plus 1. Then I would find du. Du would be the derivative of that. That would be 8x cubed. Don't forget this dx. That's worth a point alone usually. So you can't just write 8x cubed. You got to have that dx in there because you're not just doing du. You're doing du over dx, but then we bump it to the other side so that we can merge stuff together. All right, so let's look up above. So let's see what we have and what we want. So I want this thing to become a u. Okay, that's not going to be a big deal. I can make that into the u. But then we need to have 8x cubed dx. Remember the one that we just did? Du was 2x with a dx. Well, we had a 2x with a dx. We had it all there, so we could roll these two pieces, became the du down here. So I had exactly what I needed to make du. I needed a 2x and a dx. I had a 2x and a dx, so that means I could make a du. Here we don't have quite the same scenario. What do I need to make a du? I need an 8, an x cubed, and a dx. Well, I've got the dx. I've got the x cubed, but I have a 3 instead of an 8. So that's okay. That's okay. I'll show you how to handle this. So I'm going to leave a little note here off of the 3. It's okay to be off by a constant. We're going to fix that, doing some factoring out, doing some creating things with reciprocals. That's going to be okay. Put a little star there. I'm going to put another star underneath it. It's not okay to be off by a variable. So let's say I needed x to the 3rd and I only had x to the 2nd. We're in big trouble. We're in big trouble. That's not easy to fix. The constants, they are easy to fix because we can just kind of manipulate the equation to get what we want. All right, so let's look at this again. So I've got my constant here. I got that 3. I don't want that 3 to be a 3. I want it to be an 8. So what I'm going to do is I'm just going to take that 3 out of there. I'm going to factor it out just like we always do. Now, Corpy calls this, he calls it a rider because it's just going to ride its way through the equation. So not going to make a difference. So I'm going to integrate. Okay, what did we want to have here? We wanted this 3. We took the 3 out, but we need to have an 8 in front of the x cubed. Well, I'm going to make an 8 in front of the x cubed. I'm going to do it in a different color. I'm going to make an 8 appear in front of the x cubed. Now that's legal. I can just put an 8 in there as long as I cancel it out. So if you want to create an 8, you would also have to divide by 8. But if I break that 8 over 8 up into an 8 and a 1/8, I can take that 1/8 out front. Corpy calls this a correction. And he calls this a rider. That constant's going to ride through the problem. The 3 is going to be out there no matter what. We needed an 8. So we needed to create an 8. Well, you can't just magically create an 8 and expect to get the same answer. So we need to correct the 8 that we had. I multiply by 8, so I'm going to correct that with a divide by 8. Now let's go back and try to implement the rest of our u's and du's. So I've got my 8x cubed sine of 2x to the 4th plus 1 dx. Okay, I don't need to make any other corrections there. So now we can start to integrate this thing. So I've got my 3/8 out front. No, I can't integrate yet. Sorry, I'm not done u du in it. So now I'm going to start to put my u's and du's, mix this thing up. So I'm going to take my 8x cubed with my dx. 8x cubed and dx are going to merge together. To make a du. So I'm going to take the 8x cubed times dx, and I'm going to those are equivalent to du. So I'm going to sub out those two things. I'm going to replace it with du. Then I've also got, remember, I've got the sine of, but what did we say? 2x squared, 2x to the 4th plus 1. We said that was equivalent to u. So now I've taken this equation that was fairly complicated up here, this integral, sorry, and I've taken the integrand and turned it into something that's super easy to integrate. The integral of sine. Now, if I'm not going to do it here because I know my trig derivatives, but if you don't, pause, go over here, write the function, and then write the function derivative for all the trigs. So sine, cosine, tan. Go through and write them out if you don't know them by heart. So we would come back over here. Now I can integrate my constants out front. What's the integral of sine? Okay, that would mean whose derivative is sine? Well, that's cosine, but it's off by a negative. So that's going to be a negative cosine of u. And I wish I would have written that a little different. That's okay. Don't forget your plus c. The problem is we don't want this thing to be based on u. We want it to be based on x. The problem was the integral of dx. So I need to do one last rewrite here to clean it all up. 3/8 cosine of 2x to the 4th plus 1 plus c. All right, I'm going to try to explain Corpy's pattern recognition move. So this is called, I'll do it in a different color here. This is called, I can't find a good color. I call it u-du substitution. You might just see it called u-substitution. I think he calls it just u-substitution. Over here, this is called pattern recognition. All right, let me see how I'm doing here. All right, so he starts off by looking at the integral of 3x cubed sine of 2x to the 4th plus 1 dx. And the first thing he does is he takes out any constants. So he knows that he's going to have some riders along the way. So his first rider, this 3 is a rider, times. Then he needs to see if there are any corrections that need to be made along the way. And we decide on a correction based on the inside function compared to its derivative and what's still outside. So the derivative of this is 8x to the 3rd. We have the x to the 3rd, so we need the 8. So we need a correction factor of 1/8. times, now we would just do the actual integral. So what's the integral of sine? Integral of sine is negative cosine of, and then we can just leave this all the same. And I'm going to go with a different color, because what don't you want to forget at the end? Plus c. He calls this the rule, sometimes the rule constant, whatever the rule is that you're actually deriving. And when we clean this up, I'll go back to purple. When we clean this up, I get my negative 3/8 cosine 2x to the fourth plus 1 plus c. Same answer. Same answer. Now, the tough part with pattern recognition is that you've got to be able to identify the pieces. You've got to be able to do a lot of this derivation in your head. So we're going to get down here, and we're going to have to derive. Well, that one's not too bad to derive, but we're going to do some chain rule on some trig in a little bit. Oof, I struggled with that part, so I couldn't do that part in my head. I will almost always do u/du. I'll try to do it both ways to show you, at least on a couple of them, until I decide to give up on that part. Okay, well, let's keep going here. So that's his. This basically is explaining all of the writer, the correction, and the rule. He's those three pieces of the pattern recognition. But u/du is a safer method, and plus sometimes you're stuck with u/du. You have to use u/du. So if I were to pick what I would be better at, I would pick u/du. So. Okay, let's give it a try. Go for it. I'm going to encourage you to pause here and see if you can do this on your own. Let's see how you did. So I'm going to use a u/du. There's lots of stuff inside. There's lots of stuff going on, but I'm trying to identify kind of the nastiest piece, the nastiest section. And I would say this is the messiest piece. And inside of that is x squared plus 2x. Now, look, there are plenty of times that you're going to try this, and this is not going to end up being something we can work with. You're going to be in trouble. That's okay. You just erase it, start over, draw a line through it, go underneath it. Okay, so now I need to derive this. That would be 2x plus 2 dx. Notice I put parentheses around that. Yes, I am going to be that picky because it's a totally different thing. If you write 2x plus 2 dx, who's attached to the dx? Just the 2, right? So you want to make sure that you are saying properly what you mean. All right, so let's look now back up above here. Do we have what we want? Well, I've got a constant. Let's take that. Let's do that part. That's the easy part. I'm going to take the constant out front. So I'm going to bump this 1 over pi out of the way. Okay, now I'm going to look for if I have what I want outside compared to the derivative. So remember, I need 2x plus 2 and a dx. Well, I've got the dx. I've got x plus 1, but I need it to be 2x plus 2. So what do I need to multiply this by? I need to times that by a 2. Now, I can do that, but I have to correct that out front. So I have a correction. I wish I would have used some different colors here, but I didn't. So I've got, this is for my du. I've got the dx. This needs to get times by 2 to make my du. So I can do that as long as I correct with a 1/2. The integral of, all right, now let's see if we've got all of our pieces. So this got multiplied by 2, which we corrected with the pink, and it got multiplied by dx, so that became my du at the end. So I'm going to write that in pink. Then I've got my actual inside, which was u, and that's getting cube rooted. Well, I'm going to clean that up right now. I'm going to make that u to the 1/3. So these two things became the du. This, the u got put in there and became the actual integrand. Then the 1 over pi got bumped out, and then the 1/2 was a correction because we needed a 2. We have something now that's super easy to integrate. So let's integrate this thing. Let's go back to orange, I guess. So I've got 1 over 2 pi times add 1 to the exponent, so that would be 4/3. Flip and multiply, because that's when you divide by 4/3, you'd have to flip and multiply anyway. Why is that not okay? Plus c. All right, so let's see if we can clean this up now. So nothing cancels. So I've got 3 times the quantity. What did we say? U was x squared plus 2x to the 4/3 over 8 pi plus c. How could you check to see if this is right? If you want to do a check, take the derivative. They might also write this as the cube root of x to the 4th, right? Both of those mean the same thing. I'm not going to write them both out. You hopefully know it by this point. All right, let's try this with pattern recognition. So he starts off by writing down the problem again. So the integral of x plus 1 times the cube root of x squared plus 2x over pi dx. All right, so first move, any constants? Yes, we've got a constant of 1 over pi. So he takes out his riders, multiplied by. Now, do we have any corrections that we're going to have to make? Now, over here, we know we've already done it, but try to think through it again. We find corrections by taking the inside and doing du. Du would be 2x plus 2, which is off by a 2. So we have to correct that with a 1/2. So now in his head, he's taking care of this. He's taking care of those. And now he can integrate something to the something getting cube rooted or something to the 1/3. So the integral of something to the 1/3 is something. Be a good color here. Something to the 1/3 would be something to the 4/3 over 3/4. Why is this not okay? I didn't write plus c at the end. All right, now let's clean all this up and see if we get the same thing that we had over here. So I've got my 3 x squared plus 2x to the 4/3 over 8 pi plus c. Pretty cool, pretty cool. I wonder if, this is my first year teaching pattern recognition. I wonder if in a couple years I'll like this method better. But you'll see in the next couple examples, I don't like it yet. Now, honestly, you could probably pause here and do a lot of these. Well, I probably not the first one without me. We got to talk a little bit about what it means when you have multiple things that are inside. But after that, you should be able to do a lot of these on your own. So even if I don't encourage you to pause it, I'm going to try to remember. But if I forget, try to do it on your own as well. Actually, you know what? I'm going to stop here just so the video isn't quite so long. So we'll pick this up in another video.